So it was a great talk just before me, and then it will be interesting to compare our two approaches, which are, I would say, more complementary than opposite. And of course, what is even better is that we can express ourselves right now, and then we will discuss with Joachim in a few minutes. So that would be, I think, a very interesting topic to discuss. On our side, we are really advocating the use of quantum against the quantum threat, or maybe more precisely, the quantum threats, which will come with a quantum computer. And really, the talk I will have is really about how can we use quantum technologies to counter the quantum threats. To start with, to start with, let's go back a little bit to the quantum computer. Obviously, we had a very nice introduction already, so we don't need to spend too much time. But the quantum computer is really two sides of the coin, basically. On one side, it will make, you can do some computation much faster. You can do basically different computation you couldn't do before, which were called hard, and now the quantum computer can do them. So that's a big opportunity, and that's the main reason IBM, Google, and many others are really working on the quantum computer. But on the same side, on the other side, the quantum computer represents a threat for cryptography, which means that by being able to solve the same mathematical problems which were good on one side, they also threaten our cybersecurity infrastructure. And that's what we're going to focus today. Obviously, it's clear that the main thing about quantum computer is really the advantage. I would say the threat is coming as a byproduct, and this is what interests us today. Okay, next slide. So in order to understand the quantum threat, we need to go back a little bit to cryptography, and Joachim gave also a nice introduction, so I will not spend too much time here. But I want to emphasize one of the key ingredients he maybe didn't emphasize in this talk is about keys. Cryptography is based on two things. We discussed algorithm and hard maths. It's really that you need to hide stuff in mathematical problems such that somebody who doesn't have access to the key cannot find out what's inside. But that's why the other ingredient, which is very important, is the key. The key in cryptography is, of course, not a physical key. I put here an example, but that's really just to give an illustration. But the key is really a mathematical key, a series of numbers. And in order to have a good key, the basic stuff, the basic ingredient is that it has to be random. So one key element, I would say, if I want to joke a bit, about on the cryptography is to get a good key, a random key, and that's not so easy to do, because classically it's very hard to find randomness, and that's what I will go on explain in a moment. The other aspect that I mentioned, the mathematics, as we now know, and that was already explained by Joachim, is that this mathematical problem, which is supposed to be hard, actually will be threatened by the quantum computer. And what I want to show here in the next few minutes is that both of these ingredients, actually, the random keys and the math, will be threatened by the quantum computer. Why is it difficult? So let's start with randomness. Randomness is not easy to get classically. A classical system, classical mechanics is deterministic. So it's really hard to get randomness from something classical. The one way to do that is to get what is called external noise. So you have a system, and in order to get this noise, the randomness to this system, you actually rely on an external source, something which will come in and do something which input some kind of randomness. And I put here a waveform, for example, where you see, okay, this looks really random, and if I use that, I can get some random numbers out of that. The danger here, of course, is that this waveform or this noise coming from outside may not be so random. There may be some hidden regularities, which you can find out if you are clever enough, or maybe if you have enough the mathematical tools to find out what's hidden inside this supposed random noise. The other possibility is that this random noise can be manipulated. So it looks random, but actually somebody is sending you something in order to prevent you from getting this good randomness. So you could manipulate it, and then, of course, it's not safe anymore. And the last problem with getting external input is that in some cases you cannot get external input. Let's say I'm in a server, for example, which is shielded from the outside world because it has to be protected. How can you get good external noise for this server? What's happening if you got places where there is no human being or it's totally closed, for example, also with IoTs? So you cannot always get external noise, and therefore to rely on that to create a randomness may not be a best idea. That's why another way to get randomness from classical system is to look at chaotic system. Chaos is very good. You start with a system and you let it evolve, and very quickly, because it's chaotic, the state of the system is totally unpredictable. But in fact, it's not totally unpredictable. As you know, for example, a chaotic system is the weather. The weather is a chaotic classical system. We don't think there is anything quantum there. However, although it is chaotic, it means that it will evolve in a way which you can really predict for a long time. You still can predict it for a while, and you can predict it better and better. So this chaotic behavior can be used, but there is a risk that a better model, some better mathematical techniques can be used and can enhance the predictability. So what you thought was random may not be so much random. And of course, that's where the quantum computer may come in, because the quantum computer will enhance very much artificial intelligence and make better modeling. You may really, it's possible that you can use a quantum computer to predict chaos in a much better way, which is why we advocate not using classical system, but to rely on quantum. As you probably know, quantum is non-deterministic. And this was one of the facts that Einstein had difficulties to accept when he said, God does not play dice. We now know, we don't know if there is, but somehow God will play dice in quantum mechanics. Okay, and that's why we advocate using what we call the quantum random number generator, which I will describe in a minute. The other aspect we discussed is about the algorithm, the mathematics. So some time ago, before Shor's algorithm in 1994, everybody believed that factoring was a hard problem. And then Shor came and demonstrated that at least this one doesn't work. This is why we need to find new problems which would still be able to be used for cryptography. There was another algorithm, Grover algorithm, found a little bit later, which is also attacks some cryptographic aspect. But let's say this one is not so much a problem. By increasing the key length, you can still recover safety. This gives you two examples of something totally unexpected. Before these two algorithms, nobody would expect that quantum could do anything against this strong algorithm. Now we know they can do on this one. We know that factoring is not safe. And that's really what started the whole story about replacing our current infrastructure by something new. So, when do you need to worry? I think that's a very important question. We now know that a quantum computer will destroy our current cryptographic system because it will destroy, for example, through Shor algorithm, it will destroy the factoring stuff we are using. So when will this happen? I call it the Q day. Okay, the Q day is the day there is a quantum computer big enough to do some cryptography. As Joachim said, there are some small quantum computers, but we expect that they are not big enough, large enough to do real cryptography today. So there are two aspects. Before this Q day, there is already a very big risk today that about confidential information. If today you send confidential information through any network which is not protected, at the same time you send also the secret key, the key which is opening this secret if you encrypt, but this key is sent together, hidden with our algorithms. And if later a quantum computer can break that, it means that all the information which you believe would be secret for a while will suddenly become non-secret. So that's the risk today. And I think we need to know that very clearly. And that was already mentioned by Joachim in his presentation. So the quantum threat is today threatening confidential information which you send over any network. You know that by the time there is a quantum computer, this information will not be secret anymore. After the Q day, it's a totally different story. After this day, the whole security infrastructure will break down if we don't do something. We cannot do any authentication anymore. So whenever you try and download the software on the internet, for example, it can come from anybody. You cannot trust that the signature on this algorithm, on this new software, is the right one. People can impersonate you in your bank account and so on. So there is really these two different threats today on confidential information. And once you have a real quantum computer cryptographically useful, then it's the total breakdown on the infrastructure which you really need to address. So if we go, yes, how to do that? There are two ways to address a quantum threat. We call them quantum safe solutions. The first solution is to use classical solutions. So the current algorithm which we're using are broken. Therefore, we will find new algorithms. We will find new problems, new mathematical problems which we hope are secure. And that's really all the idea about what Joachim mentioned, which is known by NIST as post-quantum cryptography, replacing this broken algorithm by new ones. These problems today are expected to be resilient to a quantum computer. However, if you remember what I said before, if you send some confidential information, what is interesting for us is to see what's happening in the future. And therefore, how do we know that the algorithm we will use to send our information will remain safe in 5, 6, 10 years after we have a quantum computer? And that's a big problem. We know what we believe we know, we hope we know what we have today, but here we need also to know what will happen in the future. We need a really good crystal ball. And that's why we believe also we need post-quantum cryptography. It's very good also to have other means, and that's what I call quantum versus quantum. It means that we should also use quantum systems because they have different properties, and we can use them against the quantum computers. If you look at these systems, you see that we have, here I put a few of them. The first one is a quantum random number generator, which we can use already today to get better keys. Second one, I will discuss briefly quantum key distribution. And later on, we will go on and have more quantum, even in quantum network, and ultimately in the quantum internet, which will give more and more possibilities. So if we move to the next slide, let's start with quantum random number generators. As I said, you cannot really trust, or you should not entirely trust, classical systems to create randomness. However, quantum systems can give really good randomness. And now you can get that in a very, very small format. At IDQ, we have now a quantum random number generator, which is a few millimeters size, and can be put, and has been put, in a mobile phone. So you can get the randomness now in a totally isolated system. Remember, I told you that's important, that you can get randomness from something which is not linked to the outside world. So within this very, very small chip, you have a pure quantum generator, which will give you the randomness you need to do whatever you have, which is high security. So I believe already today, quantum can be used in order to get the best possible randomness. The next thing we can do is quantum key distribution. We don't have time here to explain all the details about quantum key distribution, but the idea is to generate secret keys on both sides of a link, as I show on this picture, in such a way that any eavesdropper which want to find this secret key will be discovered. So quantum key distribution cannot prevent eavesdropping, but it's the only solution, the only technology which allows you to know if there was an eavesdropper, and if you see there is no eavesdropper, you know the key is safe. So you can actually exchange keys from one point to another with some limitations in distance, for example, in such a way that you know, can I use the key or not? And we give a very clear result. Yes, the key is safe, or something happened, this key is not safe. Actually, in our case, with our system, we don't even distribute the key if it's not safe. And that's really unique, and that's coming from the properties of quantum, which I don't have time to develop further today. Next. So what's the status of quantum key distribution today? My colleague Olivier will discuss that later with you in a moment. Today, what I can say is that it's already available. So you can use quantum key distribution in some instances, not everywhere. And you do have some initial application, which my colleague will discuss with you. And we already, so this is for short distance now, but we're already building much longer distance with quantum key distribution backbones. And I'm sure we will discuss that in our panel in a moment. And we also plan a worldwide coverage with quantum key distribution through satellite. So quantum key distribution is a new technology which has some application today, which can be used in instances today where you want real security, but we will expand that to be able to address more and more use cases, I think, in the very near future. Next. There have been a lot of discussion about what's the difference between QKD quantum key distribution and post-quantum. And I wanted to give you just one last slide about that to tell you what's the main difference. Any kind of computational security which depends on computational power has an expiry date. If you look at the curves here, it's going down with time. If today I make a transaction on the internet, I know that in a given time, this transaction will not be secure anymore. And the reason is that you will have more and more powerful computers. You will improve the algorithms. So everything will go down with time. And if there is a quantum computer, and that's one of the curves I have here, it will drop down much more dramatically than we expected, because the quantum computer will completely break the algorithm which I'm using. So basically, the message here is that any kind of computational security goes down with time. Quantum key distribution does not. If you exchange a key today, if it's safe, it's a given level of safety, the level of safety will never decrease with time. So you're sure that you will keep the safety once you do it at the same level forever. On the last slide, what are the key takeaway points I wanted to give you from my presentation? The first one is that quantum computers will most probably break the cryptography infrastructure in 5 to 10 years. I think we are now, most of the community is aware of that. But the quantum threat is not the future threat. It's a threat already today on confidential information. This is now. Whatever you exchange on the internet now on non-secure network will be damaged, will be known as soon as there is a quantum computer. Therefore, there is a need now to start developing quantum safe security, also for confidential data, but also because, as Joachim said, it will take time to do it right and to have them ready. So the suggested steps we would like to bring to you is really, first of all, make sure that you have good key generation, and we believe quantum random number generator is a good way to do that. Adopt as soon as possible post-quantum, or even better, hybrid system, which is a mixture of different systems. And we go back to the cryptographic agility I think Joachim mentioned. I think that's very interesting because you never know the way the decrease in time will be, and therefore you need to take precautions about that. And of course, add QKD for this very high-valued confidential information where you need long-term security, long-term confidentiality. Okay, so that's my presentation. Next slide, please. And I think we will have questions later during the panel. Thank you.